All right, ladies and gentlemen, class recording has started. So today, we want to, or I want to, I don't know if you guys do, but I want to, finish up talking about Newton's laws, and we'll talk about Newton's third law. Newton's third law is a little bit different than Newton's first and second laws in that it requires two objects. It deals with the interaction between objects, where Newton's first law and Newton's second law just deal with a single object. So, before we get into Newton's third law, right? Newton's first law, summary, one word, inertia, right? Newton's second law, what does it deal with?
Acceleration.
Acceleration, and we talked about the two things that affect acceleration, net force and mass, right? Good there? All right. Newton's third law, like I said, doesn't deal with a single object, but deals with the interaction between objects. And if Newton's first law is inertia and Newton's second law is acceleration, Newton's third law is known as action reaction. And so, little premise for today, right? Blue girl, stop pushing me. Now striped girl, you stop pushing me. This will be hilarious in like 5 minutes, just so you know. This is going to be like funniest joke of the day. So, let's talk about Newton's third law, and it states, when one object exerts a force on a second object, the second object exerts a force on the first that is equal in magnitude but opposite in direction. When one object exerts a force on the second object exerts a force on the first that is equal in magnitude but opposite in direction. You guys may have heard this before, stated as for every action there's an equal and opposite reaction, which is true, but that's not quite as descriptive as maybe this is. Okay? So, these forces that are equal in magnitude, opposite in direction, we call these forces action-reaction forces. So Newton's third law deals with action-reaction forces. Action-reaction forces, like it says, are equal in magnitude, but opposite in direction. So, let's take a look here at this situation. Okay? Here's striped girl and here's blue girl. Okay? Referring to, their shirts that they're wearing. Okay? So, first thing that happens, striped girl pushes on blue girl, and blue girl experiences a force. So what's going to start happening to blue girl? She's going to start moving in towards the right. Okay? But, and here's where Newton's third law comes in. When striped girl exerts a force on blue girl, automatically blue girl exerts a force back on striped girl, even though she didn't actively push. Alright? So striped girl exerts a force on blue girl, but according to Newton's third law, blue girl automatically pushes back on striped girl with the same force, but in the opposite direction. Automatically without even trying. And that pair is called the action-reaction pair. Striped girl pushes on blue girl pushes on striped girl. Now, as we discussed, right, if we're just looking at this picture, what's going to start happening to blue girl? She's going to start moving to the right. Well, now, we've added another force in this picture, but that force is on striped girl. So what's going to start happening to striped girl? She's going to start moving to the left. So in this case here, both girls end up moving, but they end up moving in opposite directions. Now, just because they feel the same force, does that mean they move the same amount? No. The start of them moving we call acceleration. But Newton's second law tells us what about acceleration? It depends on mass as well as force. So they both experience the same force, but that doesn't necessarily mean they move the same amount, right? Because we have to factor in the mass into that whole description there too. So remember that for a little bit later on, okay? Good? All right, so one of the things that happens with Newton's third law is that people hear it and they make an assumption that they shouldn't make. And so we have to tear that down and make sure we realize why that's not the case. So if you hear forces are equal in magnitude but opposite in direction, if you've been paying attention over the past week, that should say something to you, right? If we have forces that are equal in magnitude but opposite in direction, what does that sound like? A net force of 0. Does that make sense? Right? And net force of 0 means what? No acceleration. So if Newton is telling me that forces come in pairs and they're equal in magnitude but opposite in direction, but equal in magnitude and opposite in direction mean net force of 0, what is that sort of hinting at? What should never happen? Nothing should ever change, right? And so to illustrate this problem, we're going to use a comic strip because that's kind of fun, right? So you guys have this comic strip there. It is about a horse, and it's about a talking horse, right? So the talking horse is attached to a cart, and the farmer says, "Giddy up, pull this cart so we can get going." And the horse says, "No, not going to do it." You know why I'm not going to do it? Because nothing's going to happen, right? For me to pull this cart would be a futile effort. We know what futile means? It means like not worth it. It means like you can't win, basically. Yeah. So useless. So the horse then goes to explain his reasoning. He goes, "Hey, if I pull on the cart pulls back on me. By Newton's third law, those forces are equal and opposite, and they'll cancel out. A 0 net force won't get us moving." So let's examine the horse's reasoning, and let's see if he has a valid point. So, horse says he's going to pull on the cart. Okay? And don't worry, we can finish up this drawing here in a second and get all the things we need to. So let's just focus on this picture right here. So, horse says he's going to pull on the cart. Newton's third law says if the horse pulls on the cart, what automatically has to happen? It gives us that. Those forces are equal in magnitude but opposite in direction. But do they cancel each other out? Correct answer is no, by the way. All right. And here's why. Okay. So, here's the farmer in his cart. Does he have a force on him? Yes. Will the farmer start moving because of this force? Yes. Which way? To the right. Here's the horse. Does the horse have a force on him? Yes. Will the horse start moving because of this force? According to this picture, which way would the horse move? To the left. Okay? So, do those two forces cancel each other out? No. Why not? What tool did I use to help me illustrate this problem? The spotlight. What does the spotlight allow us to do? Look at one thing at a time. Right? Are these two blue forces the same magnitude? Yes. Are they opposite direction? Yes. But what makes them different? Where are they acting? One of them acts on the cart. One of them acts on the horse. Can two forces, even though they might be equal in magnitude but opposite in direction, cancel each other out if they don't act on the same thing? No. So that's why action-reaction forces don't cancel each other out. So the little lines there on the side. Action-reaction forces don't cancel each other out because they don't act on the same object. They act on different things. So that's how we get around this problem. Yes,
so
Jim?
if I grab a pencil and start to move up,
hold on to that thought just for a second. All right, so now, if this was the situation, what would happen? If this represented the entire situation of the horse and the cart, Alec, what would happen? The cart would run into the horse. Where? Behind it. In the same spot where the horse is right now? No. Somewhere in between, right? Is that what you were trying to say? Right? They're going to run into each other somewhere in between. But does that happen in real life? No. So this isn't the whole story of the cart and the horse, right? We have to add this part of the story. If the horse is going to move forward, there has to be another force. And how big does that other force have to be? Bigger than blue, right? So we have to add a red force. Where does that force come from? So you have something to push off of. You push off of the ground. So this situation isn't complete with just the horse and the cart. We also have to add the earth into this situation, not to scale. Okay. Right? In case you were wondering, right? It's not a giant horse and a giant cart. Right? So the horse has to feel a force in the forwards direction. But if there's a forwards force or to the right, what else has to be somewhere on this picture? If there's a red arrow pointing to the right, what else does there have to be somewhere on this picture? A red arrow pointing to the left. How big is it going to be? Same size, but in a different direction. Can it be on the horse? No, because that red forces are action-reaction pairs. They have to be on different things. So that red arrow shows up here on the earth. Right? Every time you take a step, you push on the earth. So what does the earth then do to you? Pushes on you. How hard? Same amount, but in the opposite direction. Right? That's all walking is. You push on the earth, it pushes back on you. Do those forces cancel each other out? No, they do not. Right? They're an action-reaction pair. They're on different things. All right, Jack, you asked a question before, right?
How should we draw this?
You might be a good idea for good to draw that, right? Like this is the whole situation here, right? And the end result being that action-reaction forces don't cancel each other out because they act on different objects. They don't act on the same object. Okay? All right, good there.
Yes.
This leads us then to a question all the time. So, getting back to our tools, here's my spotlight tool. Okay. And I'm going to drag my spotlight tool. Oh, wrong one. Oh, that goes back to the same. Oh, there we go. Did you learn that in computer apps? All right. Here's my spotlight tool. Right? What is my spotlight tool showing us here? The earth. How many forces does the earth have on it? One. So what's going to happen to it?
It's going to move.
It's going to start moving, right? It's going to accelerate.
Okay.
So every time we take a step, what should happen? Earth should move. Does it?
Yeah.
Ready? Feel it. Ready? Feel it? Whoa. Okay. So, does it happen? Or does Newton's third law not apply in this case? How much the Earth moves, its acceleration, is not solely determined by the force it experiences, right? What else do we have to consider when figuring out somebody's acceleration? The mass. While me and the Earth, or in this case the horse and the Earth, feel the same force, they don't have the same mass, right? The mass of the Earth is very, very big. The mass of the horse is relatively small. If the mass of the Earth is really, really big, what does that mean for its acceleration? Very little, because mass and acceleration have an inverse relationship, right? So, that then leads us to the next question. Somebody's got the next question. I bet you it's going to be Jack. There's like 3 questions in this logical progression of the course of this lesson. So, first question was, if I take a step on the Earth, does the Earth move? And the answer is yes, but is it enough for you to perceive? The acceleration is so small that we don't perceive it. So the next question in this logical progression then is...
I love this bit, but is the Earth ever going to run into the moon?
That wasn't the next logical question. I don't think there's enough time for that to happen. The moon is actually slowing down a little bit, but I don't think we're gonna be long gone by the time that happens. So, yeah. All right. So if I take a step and I move forward, does the Earth move backwards? Yeah, it does. Is it enough for you to perceive? Nope. What's the next question?
What if everybody jumped on?
What if everybody jumped at the same time? Okay. Okay. So, Chris. Good job, Chris. That's the next question. All right. So let's do this. And the answer is, well, you guys tell me. What if everybody jumped at the same time?
But it's just going to stay the same. Different directions.
If everybody jumped at the same time, nothing happened. Wait. That's the next question.
It's 7 billion people in one city.
So, right? If everybody on the Earth jumped at the same time, right? Or took a step at the same time, right? People here in North America are canceled out by people here in Australia, right? So if everybody took a step at the same time, is anything going to happen? No. But now that one is not because of the mass idea. In that case, the Earth is feeling several forces. Do those forces cancel each other out? Yes, because they're all acting on what? They're all acting on the Earth. So in that case, net force 0 and the Earth doesn't go anywhere. Not because it's so big, but because the forces from different sides all cancel each other out, even though the people aren't evenly distributed on the Earth, but for our purposes of going.
What if every person was in the United States?
All right, so.
What if one person was in like South America?
Okay, or, I mean, that would pretty much be the same thing as what?
Well,
Yeah,
everybody else would jump and that person jump through it to jump through. No.
Here, let's do this. Okay? All right. So, I read something somewhere. It was one of those. Did I give you guys that science quiz the other day? Like what you're supposed to know about science?
Yeah, we got perfect.
Yeah, you guys got okay. So, in a quiz somewhere along those lines. So there are approximately 7 billion people on Earth. A little over 7 billion people. Okay. Yeah, something like that, and it keeps growing, and that's not really good for us because we're. Yeah, we wouldn't be able to feed all of them. Yeah, that's kind of the problem with all these the extra people is that we don't have unlimited resources, and so Yeah. Anyway, that's a story for a different day. What I read in one of those quizzes, and I don't know if this is true or not, but I suppose we could figure it out if we did some math or a lot of math, but it's actually not that much math. But that if all of the people in the world, 7.3 billion people, whatever it was, okay, if we could stand like right next to each other, we would fill the city limits of Los Angeles. And that's it. That's it. So, see this dot on the Earth? It says Los Angeles right there, right? All 7 billion people could fit inside of that dot.
Let's try it.
I mean, we could do some math and figure it out. But but they don't all stand right next to each other. You know what I'm saying? Like, so, but, and that was only on like one small section of downtown, right? It wasn't all like, but what they're saying is the space would be equivalent to the space of Los Angeles, but without like all the buildings and stuff. You know what I'm saying? Like, yeah, like if it was just like an open space with no building. No. Like, yeah, just like the area of Los Angeles without all the buildings, all 7 billion people could fit in that space. Okay? But for our purposes, that actually helps because we are applying a force in a very concentrated location, right? So would it move? Well, after years and years and years of answering that question with I don't know, I finally figured it out one year, and so this is what I figured out. So let me see if I can find it because I've done these calculations before. So let me see if I can actually find it here. Let me pause this. All right. So, sorry if you were watching the video. I can't find it right now. I'll look for it today, and then so I can show it to you. So I can show you guys the numbers. But the end result is I calculated it, and if everybody in the world jumped at the same time, the Earth would move something like 0.0003 meters. That is upsetting, isn't it? But it also shows you how massive the Earth is compared to us.
Well, it took like 5 big jumps each person.
I mean, see, now that's the thing, is that, okay, so if everybody jumped, we would move the Earth, right? But what happens to you when you jump? You go back down. So the same thing happens to the Earth. So you jump and you go up and the Earth goes down, but then what pulls you guys back together? Gravity. So you end up right back where you started. So taking 5 big jumps just goes, you know what I'm saying? Okay. So the end result is, say, technically, yeah, right? He would be 0.0003 meters higher, yes, like, you go. But that also shows you how big the Earth is compared to, I mean, how massive the Earth is. But in the big picture of things, when we talk about, like, you know, the solar system or the universe, the Earth is just like this tiny speck. All right. So to wrap this up, let's finish up the comic strip because the farmer, he throws some shade on the horse. All right. So it says here, the farmer goes, "No, wait a second. Easy, easy." He says, "Just push backwards on the ground. By Newton's third law, the ground will push forward equally on you, and I'll just simply follow along," which is what we showed in our arrows, right? And so the farmer, he taunts the horse, and he's like, "Hey, this ground is doing a great job," because it's not the horse that's pushing him forward, right? It's the ground that's pushing him forward. Yeah. And so the horse then replies, and maybe it's something that you guys have experienced before, or maybe like you will when you study for the test. Physics grumble physics, which, you know, sometimes shows up. So, all right, tomorrow we'll talk about conservation of momentum. We'll look at some examples and use Newton's third law, and we'll go from there.
Is the Earth getting heavier?